So for everybody who maybe is not familiar with that term, hopefully we all are, AC stands for alternating current. So alternating current waveforms, alternating current circuits. And so who can tell me what the difference between direct current and alternating current is? What's the difference there? Yes, in the front. Oh, you get the next question.
Direct current has a constant supply, which is alternating, which goes back and forth between positive and negative.
Yes.
And because of that, they have certain properties specific to each one of them.
Most definitely. There's two ways in which these terms are used. I'm going to use sort of the common definition of AC versus DC, which is that DC is always a straight line and AC is always a wave. Actually, there can be, I'm not going to go into it too much right now, there can be waves that are DC if it doesn't switch, if it doesn't cross the x-axis. But let's keep it simple for the purposes of this lecture. So what is an AC waveform? Let's take a look at one and talk about the properties of it. So an AC waveform, we can draw a very simple one here. Now there's several different ways that we can talk about the x-axis of an AC waveform. We can do it in terms of time, we can do it in terms of degrees, and we can do it in terms of radians. So give me 1 second here. 1, 2, 3, 4. All right, so we know that the endpoint, so if we label this in degrees, the endpoint, or the point at which the wave repeats, is 360 degrees. If we do it in radians, then what we have is the endpoint being 2 pi. We have the midpoint being pi, 3 pi over 2, and pi over 2. And then we can also do it in terms of time, where time, the final point we'll call t, which is the period of the waveform. You have t divided by 2. You have 3t, sorry, divided by 2. No, divided by 4. That's where I made the mistake. Okay, and then this would be t divided by 4. So this here is going to be in degrees. This is going to be in radians. And this is going to be in terms of time. We'll do problems in all three domains. Normally, it really doesn't make much of a difference because all you have to do is you can do the problem in terms of radians or degrees, and if you're given the frequency or the period, then you can just convert very easily from one to the other. Okay. So this is this is going to be, so here, 3, 6. So this is going to be the amplitude of our wave. So we'll call this VA. This down here is minus VA. Note that there's a difference between the term amplitude and magnitude. We're going to talk about that in a second and what that means. All right, so now let's draw the wave. So I'm going to draw the wave starting right here, as opposed to starting at 0 degrees. Okay, and so this is going to be our our phase shift. I'll use theta. And so phase shift refers to shifting the waveform right or left on the x-axis. Right? So if theta were equal to 0, then the wave would start right here at 0 degrees or at t equals 0. Give me a second to draw this wave. I'll try to do as good of a job as I can. Regardless of how we draw it, the difference between here and that same point that it repeats will be that 360 degrees. Now, one thing to note is that this right here this is relative. Okay, there is no absolute t equals 0 in the real world. So when we talk about phase shift, normally, well not normally, we need to be comparing that to a reference waveform. So for example, the phase shift here of theta is in reference to a second waveform, which let's say I drew like this, which starts at 0. So this is the phase shift. We're measuring the difference between the starting points or the 0 crossings of those two waveforms. Now, how do we write this mathematically? We can use, so we have this wave drawn such that it has a value of 0 at the beginning, quote unquote, where theta is equal to 0. And so that would denote which, a sine or a cosine. Which one starts with a 0? Sine, right? Okay, so what we have is v of t is equal to, actually I want to give myself a little bit of space, I'll write it below. So what we have is v of t is equal to our voltage amplitude, right, times sine of omega t plus whatever our theta value is. I can also write this, I'm going to go back to calling this phi. We can also write this in terms of just the angle, where this would be VA sine of whatever the angle is plus phi. All right, so there's multiple ways to write these equations. Okay. Right. So, first question I want to ask you is there an easier way to represent this waveform? There's a lot of information. If you look at this figure right here, there's a lot of information there, okay? The voltage at each point in time and all this type of stuff. But in reality, we only need a couple of numbers in order to describe the waveform pretty completely, right? If I tell you what the frequency of the waveform is, and I tell you what the amplitude of the waveform is, and I tell you what the phase shift is, you could draw the waveform very easily. So we're not going to get into that just yet, but what you'll see is that there's a much easier way to write this waveform than this version right here, and we're going to call that a phasor notation, where we're going to, or a frequency independent notation, where we're going to just keep the important, or the values that are most fundamental to describing the sine wave. Okay, so like we've done several other times, we're going to jump into a couple of examples. And they're going to illustrate some ideas about working with these waveforms. The first thing we're going to talk about is looking at the frequency, calculating the frequency and determining the phase shift between two voltages. Okay, so let's say we have two waveforms. They look like this. We have V1, and that has a value of 12 times sine 1000 t, whoops, plus 60 degrees. And one quick thing here that I probably should highlight is that we have frequency, which can be written as omega. This is in radians per second. We can also write the frequency as F, and this is in hertz, or per second, rotations per second. This, if we have an angle in hertz, we can convert it to radians per second by multiplying by 2 pi f. Similarly, we can also describe the frequency in terms of time. So this is going to be in seconds. And so time, or the period, is equal to 1 over the frequency. So both of these are frequency, and this here is the period. For problems, you want to make sure that you're aware of the difference between omega and f, and make sure that you're using the correct one. Okay, so going back to this problem. Okay, so a couple things that are going to make this a little bit interesting. One is the fact, the fact that this is negative is going to make the problem a little bit more difficult to deal with, because we can't do a direct comparison between these two. If these were both had a positive amplitude, and if both were sine functions, then it would be really easy to calculate the phase difference between them. You could just subtract the difference between their phi values, which is inside of the orange circle right there. However, that's not what we have. We do have a negative amplitude, and we also have a sine versus cosine problem. All right, we can write things as cosine or sine. That's fine. But if you look at this wave right here in the blue, if I were to start at, or if I were to use a cosine description, it would drastically change the way the waveform looks, because it would start there with a value of 1. And then it would be a different looking wave. Fortunately, there are some trigonometric identities we can use to go back and forth between sine and cosine. So we can shift everything to one type of function. So, again, our goal here is if we have one function that looks like this, and we have another function that looks like this, we want to figure out what is the phase difference between the zero crossings of those two waveforms. This is the value that we're looking for, is that right there. All right, so I'm going to calculate the frequency in hertz because I want to know what the period is. And the reason why I want to know what the period is because I want to get this phase shift. I want to get the phase shift in radians, in degrees, and I also want to figure out what the actual time difference is between the two zero crossings. So if I don't know what the frequency is in hertz, I won't know what the period is, and that means that I won't be able to put this in terms of time. So we know that, right, F is equal to omega over 2 pi. And we know that this will be 1,000 over 2 pi, which is, not approximately, is equal to 160 hertz. Okay, next. We want to, what I'm going to use the term, standardize the form of V1 and V2. And I'll say such that both have a positive amplitude and use the sine function as opposed to the cosine function. And so for this, we will use some trig identities. Like many times before in this course, there's a little bit of a shift in gears here. All right, we went from talking about circuits. We're still talking about circuits. Maybe we're taking a little bit of a detour, but we went from talking solely about circuits, scalar numbers, getting you used to the ideas of resistors and voltages. Then we went into nodal and mesh analysis, which had a little bit more of a linear algebra feel to it. Okay, and then we went into amplifiers, which again had its own little sort of flavor. Now we're shifting gears again, where I'm asking you to learn, to think about trigonometric identities and waves and all that type of stuff. So this is another point in the course where I think there's a little bit of a shift in gears. This is stuff that you should have seen before. I know I say that several times throughout the course, but this is something you should have seen before. So hopefully it seems familiar, and by doing a couple examples like this, it'll be a nice refresher. Okay, so the trig identities that we're going to use one that is sine of omega t is equal to -1 sine of omega t plus 180 degrees. Okay, so what we're saying is that if we have a wave that looks like this, then I flip it upside down. That's the same thing as taking the same wave, the one right here, and shifting it 180 degrees, either to the right or to the left. Actually, it doesn't make any difference. Because if I take this blue waveform and I move it over here, so this is 0, this is 180, and this is 360, and I start it here, right? The adding 180 degrees is the same thing as flipping it upside down. So that's the first trig identity that we're going to use. The second trig identity we're going to use is that sine of omega t is equal to cosine of omega t minus 90 degrees. That also makes sense if we take a look at a very simple example. So let's say we have a sine wave. So this is 180, this is 360. So a sine wave will look like this. A cosine wave will start at 1 And so it will look like that. How can I make the cosine wave look like the sine wave, or the sine wave look like the cosine wave? Is by taking this. So this is 0, this is 90 degrees, this is 180, this is 270, and this is 360. So if I take this waveform and just push it back 90 degrees, right, there's a 90-degree difference there. It'll look like, or it'll be equivalent to the sine wave. So these are the two trig identities that we are going to use. They'll be on your cheat sheet, but you should be familiar with the role that they play and how you are going to use them. Okay, so I think we'll be able to really quickly finish this up and get into the quiz. So what we see is that V2 will be equal to -6 cosine of omega t minus 90 degrees plus 90 degrees plus 30. Now, why did I do that? Because what I want to do is I want to get something that looks like this up here. So I subtracted out a 90, and I added a 90 back in. The two of these together, right, they cancel one another out. These two together give us 120 degrees, and this gives us omega t minus 90 degrees. So what is the result? We end up with -6 cosine of omega t minus 90 degrees plus 120 degrees. And so now, if I want to turn this into a sine function, all I have to do is apply that identity there, which means that we'll have -6 sine of omega t plus 120 degrees. Right? I replaced the omega t minus 90 with an omega t, and I replaced the cosine with a sine. Okay, lastly, what we have to do is, so these three steps here, these get rid of the cosine. And then now what I want to do is I want to get rid of the sine. So I'm going to do something similar to what I did before. I'm going to say -6 sine omega t. And actually, I can just go ahead and flip it. I'm going to flip it to 6. I'm going to flip the -6 to a +6 plus 120. And then now I'm going to subtract out my 180. So these two go hand in hand. Right? If we're going to flip the sign, then we also have to throw the 180-degree shift in there. And so that's applying the first identity up above. And the end result is you get between two AC waves. And so essentially what we had to do there was take two different waveforms. One was in the form of a sine, one was in the form of a cosine, one was positive, had a positive amplitude, one had a negative amplitude, and make them both into either a sine or a cosine such that we could just straight up tell what the difference is between them by taking the difference between their phase shifts, right, between their phi values. Now that can only be done in that simple way if they are both in the same form. If they're both sines or they're both cosines and both have the same sign of the amplitude. I would say that it's bad form to ever write a sine wave with a negative amplitude. Generally, amplitude we consider to always be positive. So if you have a negative value, I would go ahead and do the 180-degree shift and make that value positive. And so what we came up with was this difference of 120 degrees between the two Between the two phases, between the zero crossings, yes? Okay, well then let's pick up from there. I was wrong. All right. So, step 2, might as well just start from the beginning. I think that makes more sense. So rewind. Okay. We're calculating the phase shift between two AC waves. We have this V1, we have this V2. Again, just to recap, one is negative, one has a positive amplitude, one's a sine, one's a cosine. We're going to calculate the frequency in hertz, which I guess we did do last time. And we end up with, so 2 pi f is equal to 1,000 as shown here. That's our 2 pi f. And so what we can do is find our frequency in hertz by dividing by 2 pi. So 1,000 divided by 2 pi gives us 160 hertz. That's going to come into play later when we try to find the difference between the zero crossings in time as opposed to in angle. All right, so the hardest part of this problem is getting them into the same form. So we need to standardize the form of V1 and V2 such that they both have a positive amplitude and they both are either sine or cosine. I'm going to go ahead and choose sine. So, now in order to do that, we're going to use these two trig identities right here. We know that the sine of omega t is equal to negative 1 sine omega t plus 180 degrees. Actually, plus or minus 180 degrees. And that makes sense because if you think about it, if I were to draw it really quickly, if we draw a waveform, okay, and then I draw it upside down, right, that's the exact same thing as taking that and pushing it 180 degrees to the right. They would line up with one another. The second trig identity that I'm going to be concerned with is this one. And this allows us to convert between sine and cosine. So cosine of omega t minus 90 degrees is the same as the corresponding sine. This also makes sense if you draw two waveforms. So a sine starts at 0. So it looks like this. Okay. A cosine starts at 1. So it looks like this. Now, therefore, you can see, right, that a 90-degree shift would make the sines and the cosines line up with one another. So we need to apply both those trig identities in order to get this into the right form. So we're going to start off by trying to get rid of the cosine. So what I'll do is I'm going to take the equation for V2 right here, and I bring it down right here. So negative 6 cosine, originally it was negative 6 cosine omega t plus 30. Forget about this for 1 second. Omega t plus 30. However, we want to get it into this form right here. So what I'm going to do is I'm going to subtract the 90, and I'm going to add a 90. Okay? And so I'll pull part of it out. That'll be the omega t minus 90. And then the plus 90, I'm going to push over here and group it in with the phase shift. Now, these trig identities, okay, they can have a phase shift associated with them. The phase shift would stay the same. So let's say it's omega t plus phi. That's the same as negative 1 sine omega t plus 180 plus phi. So I ignored the phase shifts, but they would be the same. Okay? Yes?
Maybe I've just misunderstood.
Sure.
Fundamentally, what is a phase shift? Like,
A phase shift is moving right and left.
from where? Like,
Exactly. So this is something we touched upon last time. It's an important point. phase shift is a reference value or referential value. So there needs to be a reference for it. It's actually a lot like voltage. Right? Voltage has no meaning if there is no reference or ground to which it's referenced. So phase shift for a single waveform, the only waveform that exists in the universe, right, doesn't exist. Okay? For example, like in power systems, which is one of the main applications where we use a lot of AC waves, there's always going to be one node or one bus, which is the reference bus. And that provides the zero crossing, that is time equals 0. And all the other phase shifts are calculated based on their movement right or left with respect to that one. So in this case, what we're doing is we have these two phase shifts, 60 and 30 degrees, which are both referred to this third wave, which defines the zero crossing, which is not given to us.
So is that 60 degrees from the standard quote unquote phase shift, or is that the actual starting graph is 60 degrees?
So the reference is 0. This wave will start its oscillation 60 degrees after that.
Okay.
So we have a third wave, which I could call V ref, which is equal to sine of 1000 t plus 0. But when we're working in degrees, we can kind of assume that's the case. It's only when we're working in time that we would need to know what is the time of that zero crossing. Okay, so going back to this right here. So what I'm going to do is group these together. So I have -6 cosine omega t minus 90 plus 120. So what that means is now I can take this and I can turn that into this. So the cosine omega t minus 90 turns into sine omega t. This stays the same. This stays the same. Right? Does everybody see how we're applying that identity? I'm going to get rid of the highlights. They're often really hard to see on the video. I'll replace. Why is it not? Okay, so now we're here. We've gotten rid of the cosine, or we've turned the cosine into a sine. Next thing that we have to do is we need to get rid of the negative. And so for this, we just need to do two things in the same step. We need to multiply the amplitude by -1, and we need to add or subtract 180 degrees. Again, you can do it in either direction. So I subtract the 180 degrees, and I end up with +6 sine omega t 60 minus 60 degrees. And so what that leads us to is this final form of V1 and V2. So the V1 is untouched. We didn't play around with that. V2, this is the new version that we have. And now that they both have positive amplitudes, they are both sine functions, we can calculate the phase shift between them relatively easily. So the phase shift, there's two. So again, the phase shift, we can calculate phi12 or phi21. The difference can go either way. Phi12 is +60 minus a -60, and then vice versa. So you end up, essentially, the phase difference has an absolute value of 120 degrees. So there's 120 degrees between them. Now, if we want to calculate the difference in time between the zero crossings, what we need to do is to calculate, so the time between the zero crossings is equal to the phase shift over 360 degrees times the period. Why does that make sense? We're trying to cancel out units. So this is in degrees, this is in degrees, this is in seconds. So degrees will go away, and we'll be left with something in seconds. Another way of explaining this is phi over 360 will tell us what fraction of the full circle is the phase shift. And if we take that fraction and multiply it by the period, that will give us the time difference between the zero crossings. So we have 120 degrees divided by 360 degrees. Instead of calculating the period, I just put 1 over 160, which is 6.25 milliseconds. And we end up with a difference of 2.08 milliseconds. Yeah, sure. We end up with a difference of 2.08 milliseconds between the zero crossings for both of the waveforms. I'll give you a second. I'll get it. Like usual, I will post the notes, so if there's something you don't get right now, you can always catch it on when it's posted online. All right. So now moving forward, we did graph these two. So let's start off first talking about how to graph V1. So V1 is a sine wave, which means that wherever it quote-unquote begins, it will have a zero value. And the phase shift is positive 60 degrees. So we start here at positive 60 degrees. Yeah. I don't think I'm going to get both the, well, if I make it small, I can get them both in the same. So we start here at positive 60 degrees. And I didn't draw the whole sine wave, but that's what it would look like, a sine wave, you know. So 60 plus 90 is 150, so that's where it would reach its peak, where it has an amplitude of 12. And then at 60 minus 90, which is negative 30, that's where it would reach its negative peak, which is negative 12 degrees. Not degrees, volts. Okay, now let's draw V2. So V2 has a phase shift of negative 60 degrees, so I'm going to start over here. It is a sine wave again, so that means it's going to start with a value of 0. And so 90 degrees later at positive 30, that's where it reaches its peak of 6. 90 degrees later, that's where it goes back to 0. And then if you kept on going, it would reach its negative. The phase shift between these two, 30, 60, 90, 120 degrees, as we had seen before. And then it's not shown explicitly, but the difference there is approximately 2 milliseconds. Make sense? So this is slightly different than the other types of problems that we're going to talk about in this section. Frankly, we're not going to spend much time discussing these waveforms in terms of time dependent values. We're mostly going to be talking about them as something called phasors, which is a frequency-independent representation. But still, I think it's important you understand how the two relate to one another. So doing a problem like this, actually calculating the phase shift in both degrees as well as seconds, being able to draw them, understanding what they'll look like with respect to one another, this is something that you should know. So you probably won't see too many problems like this. Really, this should be something that has already come up in like some sort of math course, I guess like a trig course or something. But definitely at least spend a little bit of time on this one. It's not like a one-off that you can just discount. Yes?
What is the orange arrow?
The orange arrow was just me telling you that I was drawing part of the sine wave right there. That's it. All right. So, now, you can see that was a lot of work to get a relatively simple answer, which was just the phase shift between the two of them. If we were to try to analyze circuits using this type of analysis in the time domain, it would be very, very difficult. So, oh, I just showed you guys my code, huh? Didn't show? Good. I guess can't steal it now. I'm just joking. All right. Then I would have been on the video too. Anyone could steal my personal info. It doesn't show when you hit the keys on the...
Apparently it didn't. I guess Apple updated it. I don't know.
All right, so now what's a better way of looking at these? So what is a frequency-independent waveform representation? It's a mouthful. But the idea is actually, I don't want to say simple, but it makes the problems much easier to deal with. So it's simple in that regard. So let's say I take a voltage and I have defined an amplitude, which I'm going to call this. And then it's a sine wave, and it has a frequency, and it has a phase shift, all as shown. Okay, what if I took that and I left some of the pieces of information out? So one thing that we have to say up front is that in an AC circuit, unless you're dealing with something that's quite unusual, all of the waveform, all of the frequencies should be the same. Okay? So for example, you talk about, the power that's running through the power lines and, that's used in your homes and all that type of stuff. What's the frequency of that? Sixty hertz. So that's the standard frequency for power transmission and distribution in the United States. In Europe is 50 hertz. So all of the frequencies should be the same, which means that when we do our analysis, we don't need to consider the frequency in the problem. So that's what it means when we say a frequency-independent waveform representation. We're not going to be writing the frequency each time. So then what other important pieces are going to be left? We have the amplitude. That's important. And we have the phase shift. That's important. Like I said, we don't have to worry about the frequency. We are going to assume that we know that up front. And why don't we have to worry about time? We don't have to worry about time because we can fill in those blanks later. What I mean by that is if we always have a sine wave and we know what the frequency is, getting the voltage at time equals, let's say, pi divided by 50. Well, it wouldn't be time, it would be theta. At pi divided by 50, we could derive that, right? We would plug it into the sine function and we would get that value. So when we're doing our calculations, we're going to leave that part out. So what we end up with is what's called a phasor. And so the phasor represents, so we'll call it big V. Okay, I'll use this arrow to, the superscript arrow to indicate that something is a phasor. And it's going to be defined in terms of its magnitude and its angle only. And I'm going to replace this with theta since I used theta before. So the Rms magnitude which stands for root mean square. There's an easy way to find that for sine waves. It's simply the amplitude divided by the square root of 2. So this right here, okay, we don't use the amplitude here, we use the magnitude, which in language often they mean the same thing, but in this class they are different. Amplitude and magnitude are two different things, although they're related. Now RMS, I will talk a little bit more about what RMS actually means, root mean square. This shortcut, amplitude over square root of 2, only works for a sine wave. There's some shortcuts for other waves, but anyway. So this is our phase. So what we've done is we've taken a time-varying expression. So this is a time-varying description. And we've replaced it with a phasor, frequency-independent, time-independent representation. Right? Time is not going to play a role in this. Okay. Maybe I should just go ahead and get this out of the way. What is RMS? RMS is, the name does a very good job of describing exactly what it is. Root mean square. So if I want to find the RMS, so let's call this VRMS, it's simply going to be equal to the square root of the mean of the voltage squared. And the discrete form of that (1 over n) of the sum from k equals 0 to n of v k squared, where n is the number in one period. You should be familiar with that definition. I'm not going to take the time to go through and do an example of calculating it because I feel like that's something that you should understand from your math courses. But again, we luck out that there's a shortcut for a sine wave, which is just amplitude divided by square root of 2. But you could go and get the same answer by using one of these two expressions. Okay, now, let's get down to why this is important. The reason is because it makes steady state analysis much easier. Okay. Before we get into that, are you all familiar with what the difference between a transient analysis and a steady state analysis is? Yes, kind of. So, just quickly, let's say I'm looking at this section of time here of a waveform. And here, I have an event that occurs. Something that disturbs the system. It could be someone turning on and off a switch. It could be whatever, right? So when we have that sort of situation, we go from a steady state, the event occurs, then we'll have a transient period, and then it will reach a new steady state. So let's say that we can consider this. So we'll call this T settle. So we have the point at which the event occurs and it causes a disturbance in the system, and then we have the point at which it settles. So here, from here over, this is a steady state condition. Before the event occurs, we had a steady state condition, but in the middle, right here, this is called a transient period. Because transient, things are changing, things are moving. I could draw a similar sort of analysis or similar example with an AC wave. So steady state for AC waves doesn't mean that the voltage isn't changing, because the voltage will still be oscillating, right? It'll look like this. Okay, but at the point at which the event occurs, maybe what we'll have is some disturbance, and then it'll return back to steady state. So steady state for the AC waveform just means that its amplitude is staying the same, it's oscillating at its constant frequency, and there's no, it can be described by the sine wave expression. Okay, so our phasor analysis works for the steady state periods. So this in here, we can't use the phasors to analyze this part of it. All right. So now that we know why it makes steady state analysis easier, let's take a look at an example. So let's say I have Let's say I have a circuit that looks like this. Okay, this is going to be a phasor. It has a 1 volt magnitude. It's going to be assigned as the reference, so it has a 0 phase shift. Okay, this is the reference voltage. And then over here, I have an impedance, which I'm going to define as 2 with an angle of 90 degrees. Okay. We'll talk a little bit more. This is a polar representation. This is the polar form of the phasor. There's another form, the rectangular form, which we'll talk about in a second, which is generally used to describe impedances, but for the time being, we'll just look at it like this. So we define both the impedance and the source as phasors, and now we can solve for what the current is relatively easily. So what is I? First things first is it uses the same expression that you would for any DC analysis. Okay, it's going to be equal to the voltage divided by the impedance. Okay, so it'll be 1 with an angle of 0 divided by 2 with an angle of 90 degrees. Now, in a second, we're going to spend some time talking about how to do the math with these complex numbers. Does anybody know what the answer is? What is 1 angle 0 divided by 2 angle 90? What does that equal? Anybody know how to do that? Have you worked with complex numbers at all in any other courses? Okay. Well, the answer is 1/2 with an angle of 90 degrees. And now we'll go back and we'll talk about how you come up with that. Anyway, but that's an example. That's how simple it is to solve an AC circuit using phasors. And if I wanted to write that in a time-dependent form, I would say that's going to be equal to square root of 2 times 1/2 sine of omega t minus 90 degrees. That's what I of t is equal to. Why is this equal to square root of 2 times 1/2? Can anybody tell me? Right? Yes? Well, so this is the RMS. This has to be the amplitude, right? When we're writing it in the sine wave form, it has to be the amplitude. So to go from one to the other, we have to multiply by the square root of 2. Okay. So now that we've talked about how phasors and complex numbers can be used in circuits, let's take a step back and talk about what a complex number is. Okay, so the first thing, and then hopefully this is going to jog your memory, we'll ask a couple of questions. So what is an imaginary number? Anybody remember? Yes. I, right? Is that what you said? A plus bi? Okay. Yeah, right. Exactly. So, so that's actually a complex number because it has a real portion as well. So the imaginary portion is just the second part of that. So what we have is, I'm going to call the coefficient k. So if we take k and we multiply it by the square root of -1, right? We know the square root of -1 doesn't really exist. So what we do then is we replace that and we call it k times I, although Because I is used to represent current in pretty much all engineering, especially in electrical engineering, they replace I with J. So imaginary numbers, J equals the square root of -1, and we won't be using I at all. I will stay current. So J equals the square root of -1. Okay, next question. What is a complex number? So a complex number is something plus the imaginary, right? So we have the real, we have the imaginary first, and then we have the real. And so this is what we call the rectangular form. That parses out the real and imaginary pieces. So now that we're talking about forms, what forms exist? Right? We have, I already said, rectangular, and we have polar. So rectangular form A plus JB, same thing as above. And then for this one, I'm going to call it magnitude with an angle of theta. These two are equivalent, which a lot like we use that term in for Thevenin and Norton circuits. What it means is we can go back and forth between them and they represent the exact same thing. The easiest way to represent the relationship between them is to do so graphically. So phasor we can also call it a vector because you'll see here it can be represented as a vector, right? So I'm going to call this the real axis. I'm going to call this the imaginary axis. And I'm going to go ahead and come up with an example. I'm going to say, so this is 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. So this point right here is 7, 5. I'm going to go ahead and draw a vector that goes along with it. And this vector has an angle, which is the same as the theta, this theta right here. And it has a magnitude, which represents the length of the vector. And that's the same m as above. This right here is what we were calling A above, and this right here is what we were calling B above. I put it in parentheses because those aren't permanent names, those are just the names that we were using for the moment. Actually, it'll probably be easier if I just call it this. I'll call it R E plus J I M, and then I can call this R sub E, and I'll call this I sub M. Okay. So now, if you take a look at this picture, trigonometry, right? That's the right way to say it? Trigonometry? I was getting confused with trigonometric. So trigonometry and geometry. Okay, tell us several things about this. Anybody remember what Pythagorean theorem is? Right, so we know what the length of the vector is. We know that the magnitude will be equal to the square root of the r sub e squared plus the I sub m squared. We also know that the theta will be equal to the inverse tangent of the I sub m over the r sub e. And furthermore, we know that r sub e will be equal to the magnitude times cosine of what the angle is, and we know that I sub m will be equal to the magnitude times the sine of theta. Right, so all this here included in the orange is simply just a callback to stuff that you should have learned in those classes. And so that's essentially how you go back and forth between the two of them. If you have something in rectangular form, then you're going to use this equation and this equation to go to the polar form. If you're in the polar form, you'll use the other two to go to the rectangular form. Make sense? Okay. So now, the next question we have is, how do we do math? Because if you look up here, we divided two vectors, two phasors in polar form by one another. You can kind of see the logic behind doing this division, right? Can anybody sort of try to predict, or based on what we have right there, how did I get 1/2? If we just look at it. 1 over 2, right? We divided the vector, we divided the magnitudes by one another. And -90, you could sort of guess that it was the top angle minus the bottom angle. And that's actually exactly how we do it. So the worst thing about the complex math is the fact that it's really easy to do addition and subtraction in one form, and it's really easy to do multiplication and division in the other form, but vice versa, it doesn't work very well. Trying to divide in rectangular form gets messy, you can do it, and trying to add in the polar form gets really messy, you can do it. But so the hardest part a lot of times is the constant need to go back and forth between the polar and the rectangular forms. So how do we add or subtract two vectors? I'll say complex numbers. So the first thing is that we will do this in the rectangular form. And so if I have A plus JB plus C plus JD, all that you have to do, A plus C That's it. You add the real, you add the imaginary, and that's what you get. Okay, now what about multiply and divide two complex numbers? So you will do this in polar form. And so what we end up with is A with an angle of theta A times B with an angle of theta B is equal to A times B with an angle of theta A plus theta B. Finding the reciprocal, which is really the key to doing division. So how do we find the reciprocal of a complex number, which is the same as just 1 over that number? What we have is that 1 over A with an angle of theta A is equal to 1 over A So you combine these two together to get division, right? A theta A divided by B theta B. First you would find the reciprocal, and then you divide. Or in other words, right, you divide the magnitudes and you subtract the top angle, or subtract the bottom angle from the top angle. Okay. So that's one of the more, I would say, practice-intensive parts of this chapter is getting used to doing the complex math. And again, this part of it is a huge piece. Going back and forth between the rectangular and the polar forms. Because let's say you have a problem that requires you to use KVL as well as Ohm's law. KVL is predominantly addition. Ohm's law is going to be division. You're going to have to use both forms, and you might have to go back and forth several times. Now, for here, for this one, I'm not going to talk about it. I don't think I have time today, but I will go into it. Be careful when you have inverse tangent of imaginary over negative real. The inverse tangent function can't tell when you're doing inverse tangent of -3 over +1 versus inverse tangent of +1 over -3. Okay, but those are two different angles, right? If this is 1, 3, 1, 3. So +1, -3 is down here. -1, +3 is up here. Right? Your calculator is going to only give you one answer when you do inverse tangent of -3. It's always going to assume, 99% of the time, it's going to, any calculator I've seen assumes that the numerator is the -1. So if you have a case where you do inverse tangent of +1 over -3, you have to take into account the 180-degree shift that gives you the actual number. Does everyone understand what I'm pointing out there? that'll come up in the problems, so we can talk more about that. Okay, so we're pretty much at the end here. We'll stop.